So Ben Kravitz,
Yes.
talk on SRM impacts on the hydrological cycle. Take it away, Ben.
All right. Thank you, Neb, and my apologies for the technical difficulties. I promised it worked yesterday when we tested it. So I'm going to be talking about SRM impacts on the hydrological cycle, as you can see from the title. So, of course, I have quite a few people to thank, many of whom are sitting in the room there, and really many people who aren't in the room. Thanks to everybody involved with GeoMIP. We couldn't have done this work without you. So I wanted to talk a little bit about the motivation, why the hydrological cycle. So this is a paper published by Alan Roebuck and colleagues in 2008, looking at June, July, August change in precipitation for a tropical injection of 5 megatons of sulfur dioxide per year into the lower stratosphere. It's a very similar experiment to GeoMIP's G4. And what I want to highlight is that region there. So you can see a lot of brown, a lot of reduction, and that's we attribute that to a reduction in the monsoon precipitation from geoengineering. And so this caused us to think a little bit, maybe this is something serious that we really need to look at. And that I would say the hydrological cycle was one of the founding motivations behind why we wanted to do GeoMIP. So, and it's not just model results, there are analogs as well. So this is a paper published by Kevin Trenberth and Igwo Dai in 2007, looking at how the global hydrological cycle was suppressed by the stratospheric aerosol loading due to the Pinatubo eruption. So you can see that gray shaded area there, that's the region that was affected by Pinatubo, and both continental discharge and land precipitation went down. So this is also very suggestive because we have some model-based evidence and some actual observational-based evidence. So what does this say about geoengineering? And here are some things we know from GeoMIP experiment G1. I'm sure you've seen a lot of that today, probably while I was asleep, but just in case, the G1 experiment is down at the bottom left. So against an abrupt increase of CO2 from industrial, the solar constant in models was reduced to compensate the net radiative forcing. So you can see these plots here. On the left is 4 times CO2, June, July, August precipitation. And on the right is 4 times CO2 plus geoengineering, also June, July, August precipitation. This is an IPCC figure, so the stippling indicates where the models agree on the sign. And you can see, for one, they agree in quite a lot of places. And also you can see that in the 4 times CO2 run, there's an accelerated hydrological cycle. This is fairly well known. And in the 4 times CO2 plus geoengineering one, there is a suppressed hydrological cycle, especially in the tropics. And this is a robust model finding. And now I want to show you that it's not just that if we aggregate these precipitation patterns. So there are 3 general boxes here. The left box shows global average precipitation. The middle marked GMI shows global monsoon index, and the right is the intertropical convergence zone. So the first 2 boxes in each of the larger areas show an increase in precipitation due to an increase in CO2. So that's the 4 times CO2 run. And the 2 right box and whiskers in each of the sections shows the response of G1. So you can see that the hydrological cycle is accelerated by 4 times CO2, and then it's decreased in G1. And that's not just true for global precipitation, that's also true for the global monsoon index. And actually, if you split the global monsoon index into individual monsoon regions, you see a similar result for all of those. So that was the mean precipitation. We can also talk a little bit about extreme events. So this fairly complicated plot shows a change in frequency of precipitation events. So if you look at the x-axis on the left, you have very small precipitation events, and on the right, you have very large precipitation events. So the 4 times CO2 run shows a pattern that's been coined, the rich get richer and the poor get poorer. So effectively, areas that are receiving a lot of intense precipitation events would receive even more under high CO2, and areas that are not receiving a lot of precipitation events would receive even fewer. And the geoengineering run on the bottom panel reverses that trend. So this is experiment G1 again. So you can see that it actually does reverse the rich get richer and the poor get poorer trend. So now into a little bit about the mechanistic changes behind precipitation. So this is just global average precipitation plots. So, and it's a time series. So each line represents an individual model participating in geomips. So these are the 4 times CO2 runs. And you can see initially the precipitation decreases, and then it slowly increases over the course of simulation. So we actually know something about this, and judging from Ken's title, he may have presented something to this effect earlier. So the initial decrease is called the fast response, and this is a radiative effect. So this is without changes in global mean temperature, or with small changes in global mean temperature, there are adjustments going on in the atmosphere, for example, clouds, lapse rate, things like that. And that causes the initial decrease in precipitation. And then as temperature increases over the course of simulation, you get that increase in precipitation. And so that's the 4 times CO2 run. Here's experiment G1. So we effectively get a sustained fast response due to suppression of temperature-related feedbacks. And I put this quote up here that I forget where I found it, actually. I need to remind myself of the citation, but essentially what it says is, if radiative fluxes change, then precipitation must change in a way so as to balance the total column energy budget. And I really like that because it tells us that we can look at these precipitation changes, and if we understand how the energy is changing in the atmospheric column, both at the surface and at the top of atmosphere, so the entire column, then we can actually understand a little bit about why precipitation changes. So I'm going to show you a couple of complicated plots here. I've skipped a lot of the math behind this, but basically what you can do is you can decompose precipitation changes in energy units into 2 terms. So the top panel is the mean evaporation term, and the bottom panel is the moisture convergence term. So basically, if you want to describe precipitation at any given point, precipitation can change vertically or it can change horizontally. And that's basically what these 2 terms represent. So this is an average over the first year of changes in the G1 experiment. And what you can see here is that land and ocean precipitation decrease. And if you look at the top panel, so in these 2 panels, stippling denotes where the models do not agree. It's different from the IPCC convention. And so you can see there are a lot of areas, especially the stronger areas in the top panel, that are not stippled. That means that the models show it's a robust feature of the models to show that precipitation decreases due to a decrease in mean evaporation. Now on the bottom, basically the entire figure is stippled except for a couple of small regions. So what we're interpreting that to say is that contributions from moisture convergence are in most areas small, except possibly in the tropics. We still haven't attributed a mechanism to that. Now, what we can learn further from this is that changes in moisture convergence, at least by this mechanism, are largely due to changes in mean circulation. So the Hadley cell, the Ferrel cells, things like that. So this suggests to us that changes in circulation in experiment G1 are small. We have not verified this because we're a little bit undermanned. There are quite a few studies to do. So if anyone out there is looking for something to do in terms of analyzing geomip output, we would really appreciate your help if you want to look at some of the circulation changes that are going on. So now I want to talk a little bit about some uncertainties in our results. So here are plots of the Bowen ratio, and these are fairly complicated plots, so I'm actually showing you ratios of ratios, and just to make it a lot easier on you, I've given you a cheat sheet. So if you look right below the color bar, you can see that I've said that land values greater than 1 means that it's drier than in the control simulation. And if land values are less than 1, it means it's wetter than in the control simulation. So on the left, we have the results for the 4 times CO2 run. And on the right, we have the results for the geoengineering run. And what you can see from these is the patterns on there are very similar. And what it took us a while to figure this out through a couple of idealized simulations, but what we figured out is that a lot of this is due to the CO2 physiological effect. So both of these take place in a 4 times CO2 world, and plants use water more efficiently when there's high CO2, so they close their stomata, and this reduces evapotranspiration. So that's one of the large effects here. Now, there was one study done by John Fife and the Canadian group, and they actually picked a lot of these apart in their model, and they found that the CO2 physiological effect represented about half of the surface energy budget effect in the model. So clearly this is something that needs to be quantified a little bit better. So here's a plot from a paper by Ulrike Niemeyer, where they looked at a few different methods of doing geoengineering in their climate model. So for those of you who are familiar with experiment G3, all of these are based on that. The overall goal is against RCP 4.5 to keep radiative forcing at 2020 levels. So SALT is is injection of salt into the marine boundary layer. FIX is where they just fix the radiative forcing. SULF denotes stratospheric sulfate aerosols, and SOL indicates the solar reduction. So what this is plotting is changes in evaporation over in the entire simulation. And as you can see, the results really depend on how geoengineering is done. So a lot of what I've just talked about is experiment G1, where you increase CO2, turn down the sun. That can tell us a lot, and we've gained quite a lot of knowledge from that, but clearly, from this figure at least, that cannot tell us everything. There are a lot of things that are particular to sulfate aerosol injection that solar reduction cannot model. And of course, the results of sulfate aerosol injection are likely strongly dependent on how aerosol microphysics are represented. So there are 2 important messages here that I want to talk about in terms of my results. So number 1, so if you look at this plot, on the bottom is precipitation change, and on the left axis is temperature change. The origin here is the pre-industrial control. So if you look at the distance between the origin and the 4 times CO2 run versus the distance between the origin and the G1 run that I've circled there, you can see that the geoengineered climate looks a lot more like the pre-industrial climate than the 4 times CO2 one does. And the reason I bring that up is I think it's important when you are talking about geoengineering to talk about what your baseline of comparison is. This is not a new concept. I'm sure people have talked about this this morning, but it's worth reiterating in far as important to take this into account when interpreting the results I've presented. Another point that I wanted to make is that experiment G1 it implicitly assumes that geoengineering is the only response to an increase in CO2, which is really useful for idealized experiments and figuring out how the climate system works, but that doesn't, in my opinion, that doesn't really make sense in terms of how geoengineering might actually be used if society should decide it wants to use it. So the results I've shown are in the circled area there. And this goes to a point that David was just making in the Q&A session earlier. There are many possible climates that could result from geoengineering depending upon the amount of geoengineering. So in theory, one could travel anywhere along that line. So the example that I heard was maybe no precipitation change and a little bit of increase in temperature, or maybe just go slightly down those lines with just a little bit of geoengineering. So that brings up another point, that the hydrological cycle results are highly dependent upon the amount of geoengineering. Here's a paper by Jim Haywood showing some initial steps in looking at multiple degrees of freedom in geoengineering. So what he did in his study, which he may have already talked about, so apologize for the repetition, is looking at geoengineering just in the northern hemisphere or just in the southern hemisphere. And this is geoengineering with stratospheric aerosols. So the top panels are precipitation and the bottom panels are net primary productivity. And depending on which hemisphere geoengineering takes place, you can get a shift of the ITCZ, and that really affects precipitation in the Sahel. So if you look at northern hemisphere geoengineering, there's a drying of the Sahel as measured by net primary productivity change. And if you look at the southern hemisphere geoengineering, there's a greening of the Sahel. And so that leads me to some additional work that we have done looking at sort of a range of possible outcomes. What if there were multiple degrees of freedom? So in the top left panel, we looked at different latitudinal patterns of solar radiation. And in the bottom left panel, we looked at geoengineering in different seasons. And so if you look at the right panel there, this is showing, the shaded area shows sort of a range of achievable climates if one were to look at different combinations of these different methods of, or these different degrees of freedom in terms of geoengineering. I'm not assigning a value judgment to any of these. I am not saying anyone is better than the other. What I am saying is that by only concentrating on experiment G1, you're missing a range of possibilities of geoengineering. It's not just geoengineering on or geoengineering off. There are quite a few degrees of freedom here. So that leads me to my conclusion slide, sort of a whirlwind tour of things we know about the hydrological cycle. We know some things about the hydrological cycle effects of solar reduction, and we know some things about why those effects show up in climate models. That said, there are a lot of things we don't know, especially about other types of geoengineering. And the hydrological cycle effects are not always the same as for solar reduction. The CO2 physiological effect needs to be further quantified, and according to a lot of studies out there, it could be very important. A lot of climate models represent the CO2 physiological effect. I am not a land surface expert, so it is not for me to say whether it represents those processes well. Also important to note, so my title was SRM Impacts on the Hydrological Cycle, which when I said impacts, that may have been the wrong word to use because hydrological cycle changes are not impacts. So for example, I can talk about precipitation, I can talk about evaporation, but that does not necessarily say anything about things like regional water.
I didn't do that. No, I didn't.
Engineering is done. That is, there are multiple potential degrees of freedom. So I think that's all I've got, and I'm happy to take questions.
Brilliant. Thanks, Ben. Look at the screen. Ben, can you switch us over so we can see your face rather than your slides, or that might be nice.
I can try.
Make it full screen. Oh, God. Oh, no. Make it full screen. Oh, I can see and your slides. Brilliant.
Good.
Okay, great. Sorry, that's my face. Okay, do we have a couple of questions for Ben?
Oh.
We're seeing a lot of you. Yeah, there we go.
There we go.
Yay! So, any questions in the room? Go on, we've managed the technological feat of excellent up there, of getting Ben via Skype. So, ask the man a question.
It's a bit of an offbeat question. It's hard for me to imagine a world of 4 times CO2 as being a reasonable comparison. It's so far beyond anything we know. I cannot see what's particularly reliable about the models, and it's really a world that I know we can get there, and maybe we're going there, but it's so far beyond what's manageable. Why bother?
Ben, did you hear that?
Not very well. Would you mind repeating it?
Doesn't make any sense anyway. I just said, why bother examining a 4 times CO2 world? I mean, it's useful, I know, but the consequences of the massive change in climate are so far beyond comprehension. It's difficult to know why we should pay attention to detailed modeling.
Did you catch that? So why use a 4 times CO2 world as a comparison? Your 4 times CO world is so far ahead. It's a massive amount of CO2, and it's a trajectory we're possibly on, but not necessarily. So justification for 4 times CO2. Go.
Yeah, that's a really good question. So the way I see it, it's really hard to come up with a climate model experiment that is so simple, we can't learn anything from it. And those simple experiments actually have quite a bit of value in teaching us how the climate system works. So we liked the experiment G1 because it was very easy for all of the models to do. So we got quite a bit of participation. We now have 13 models that have participated in it. And also, it's not as inapplicable as you might think. So there are a few papers out there by Peter Good, who's been looking at just how applicable the 4.2 runs are, say, RCP 8.5. And there are clever ways in which you can scale those results to get something meaningful about, say, more realistic simulations.
Okay, that's brilliant, Ben. I've got one final question, I think, or I think people might be ready for dinner. Sorry, Ben. Thank you so much for your patience. So thanks so much for round of applause, final applause for Ben, for Sebastian, and for Piers and your questions. Thank you very much.
Thanks.
Hugh?
What?
Thanks everybody today for an excellent day. I've got nothing to say. Are there any questions anyone have about this evening? Everyone knows what they're doing. Be at Lady Mitchell Hall for 7 o'clock. Go to the pub. The talk starts at 7:30, but we need to be in the room by 7:15. It says 7 on the website, on our website, or the